Okay, we're moving on from what we've done in the past. We've looked at all those horizontal springs where it's a block sitting on a frictional surface, connected to a horizontal spring. We stretch it out slightly, it moves from side to side, just the way that we're used to happening in a spring system. But now we're going to hang it just like the one that sits in our classroom. It's just going to hang upside down. We move it down a little. It'll go up, oscillate up and down, up and down, up and down. That's the system we're looking at this time. Obviously, since it's up and down, weight is a factor in a way that it wasn't for the horizontal system. Of course, it's mass mattered, but you weren't lifting it and lowering it, so that weight didn't make that big a difference. In the horizontal system, the equilibrium point is this point where none of the spring is compressed and none of it is stretched. It's where the force is zero. Well, the equilibrium point is going to be different this time. The equilibrium point is going to be at the point where the object would naturally settle. And that point won't be where the force is zero. It'll be where the force from the spring exactly matches the weight. So the spring won't be stretched out in some way or another the entire time during its motion. And we're going to measure the amplitude vertically instead of horizontally this time. We'll measure it above and below. The distance above and the distance below will be the amplitude. That seems pretty reasonable. So let's take a look at the system. Hey, there it is. There's a spring crudely drawn by yours truly, hanging from a hanging down with a mass connected to it. I drew a line for the equilibrium. Of course, when I release it, it won't be moving. Its velocity is going to be zero. And all the energy in the system is going to be elastic potential energy. I suppose you could argue that if you cut the spring, that it would fall down some distance at GPE. But we're going to call that GPE zero, mostly because it's convenient. We let it go, it flies upward. And you can see it's going upward, it's at equilibrium. It is headed up toward the top, it's moving. Now, the force on the spring isn't zero this time, though. There's going to be a force on it, and that force is holding up the spring. So it's got its maximum velocity at that point. It's headed up. Okay, but its energy is going to be kinetic. It's going to be EPE because the spring is still going to be stretched, and it's going to be GPE too because it's higher up than it was before. Okay. So it's headed upward. It's going to have all those energies at that point, which is different. Then it's going to head upward toward the top. Now at this point, you can see the spring it looks like it's compressed, but it's really not. Remember that it's just not as stretched out. Gods are good, we have not approached or are just approaching the point at which the spring is at its original unstretched length. So we're actually getting a smaller and smaller contribution upward from EPE. And because of that, gravity's having a great GPE is getting larger. It's having a greater role in the net force on the object. Okay? The net force on the object is basically getting to the point where it's not very much, where it's actually going to become not zero like it is at equilibrium, but it's becoming negative. There's not much pull upward from the spring because it's not as stretched. So the force is actually becoming a net negative force upward. So you can look at that, you can see that the velocity is zero at the highest point. And there is EPE, and there's some EPE, a small amount, a very small amount. Most of the energy at the top is GPE. There's not going to be any kinetic energy. But like I said, most of it is going to be gravitational potential. Remember, the EP is getting smaller. If we looked at the net force at that point, it would be negative. The effect on the vertical motion of the period, interestingly enough, it doesn't have an effect. Okay. It actually behaves the same way, about the same equilibrium point. If you have more mass, you're going to get a longer period. It's going to stretch the spring more, so it's going to lead to a longer period. If you have a spring with a higher spring constant, if it's stiffer, then you're going to end up with a shorter period, just like before, 2 pi root m over k. Again, the only change is how the energy is distributed and the equilibrium point. And if you don't believe me, you should watch this video. Okay. I'll put this on the, I'll share this presentation with you as well. But if you watch the video, you can follow the graphs. You can see what happens to the energy. Follow the little bars on the side. You can see that the energy changes in position as it falls and rises.